my microphone on? Can you hear me? Good evening, everyone. Welcome. Just a few housekeeping things, first of all. If I could ask that you please keep your phones on silent throughout the evening. We're not expecting any fire alarms, so if there is a fire alarm, please leave in an orderly fashion. The stewards will guide you out to the car park. If you'd like to tweet about tonight's lecture, please use the hashtag InsightsNCL. And then following the lecture, there'll be an opportunity to ask questions. There'll be microphones. I'll point to people in the audience and a microphone will come to you. So if you just wait until the microphone arrives so that everyone can hear you. Tonight our speaker is Professor Saiful Islam from the University of Oxford. He grew up in North London, obtained his chemistry degree and PhD from University College London, followed by a research fellowship at the Eastman Kodak Labs in New York. He joined Oxford quite recently, 2022, after 16 years at the University of Bath. He's well known as he presented the 2016 BBC Christmas lectures on the theme of energy. He's received several awards, including the 2022 Royal Society Hughes Medal and the 2020 American Chemical Society Award in Energy Chemistry, and he also declined an OBE in 2019. He's a patron of Humanist UK. When he's not exploring new materials, he enjoys family breaks as a dad of two, films and indie music. So could you please all join me in welcoming Saiful to the stage?
Right, I'm going to start with a thank you and then a confession. The thank you is really to all of you for coming out on a grey evening to hear about material science, and also to thank Greg and Umbreen for the invitation and for the organisation of this lecture. The confession is I'm a bit nervous about this lecture. I'm used to giving conference talks, but I wasn't sure about the audience and about the level to pitch this talk. There's professors in chemical engineering, there's professors in chemistry here, there's lots and lots of university students in science, and there's the general public and a range of non-scientists. So I wasn't sure about the content. So I asked Greg, what should I talk about? And he said, about 50 minutes. So for the next 49 minutes, I'm going to give you a flavour of green energy materials in 3D, crystal gazing on the atomic scale. And these are two typical crystal structures, and if you get your glasses on, as in life, or as in politics, red is on the left, and that's where my heart is. So, and for the best effect, if you stare at that for a while and shake your heads about, and even if that doesn't work, it makes me smile from this end. But hopefully you'll see gradually emerging two crystal images. On the left is something I'm going to touch on later on, and on the right is based on the well-known buckyball, the C60 buckyball. If you really stare at that, you can see that buckyball really coming out at you. So since I was going to talk about flavour, let's start off with the menu for the talk. So the lecture menu starts off with which materials am I going to look at and how do we model them? The main course is why lithium batteries? Why are we looking at lithium batteries? Sort of dessert is solar. What's new with solar? And then lastly, a bit of a journey. How did I get here? And then when life gives you lemons, what do you do with them? So hopefully I'll explain all that. So let me start off with the energy challenge. I think we know that the energy challenge is one of the hottest topics, both literally and metaphorically, in this century. How do we produce and supply low-carbon energy? And there are going to be alternatives to fossil fuels. Fossil fuels will be around for a while, but there are alternatives in terms of solar, energy storage, wind, etc. And we can do our bit in terms of energy conservation. In terms of, I'm not going to talk about climate science as such, but if you want a really, I think, a comprehensive report on climate change and evidence and causes, If you go to the UK National Academy of Sciences, which is the Royal Society, they teamed up with the US National Academy of Sciences and produced this evidence and causes. And it's free on the website, and there's some really good short videos as well. So what do I work on? Well, energy storage and energy conversion are probably more important now than any time in human history. And these energy devices rely on materials. So on the left is storage, on the right is conversion. And we need advances, and these advances require new materials, they require new concepts, but also a greater scientific understanding. And that, in a way, summarizes my research philosophy throughout my academic career, to look at materials, concepts, and a greater understanding. So, crystal gazing, what do these crystals look like on the atomic scale? So we live in a world of crystals, and one of the most common crystals that we all know is salt in our kitchen, the stuff that you sprinkle on your chips, on your rice, on your pasta, and in my case, before a tequila shot. And now get your 3D glasses on again. So you're going to see the well-known sodium chloride structure. So this is made up of sodium ions, which are the small spheres in this structure, and the large ions are chloride ions. And they make up this very regular crystal structure. And that's a common aspect of crystalline materials. They're very regular in 3 dimensions. This is not a molecule, so it's not an individual molecule. This unit is repeated in 3 dimensions. It's repeated in 3D. In 2D, they're related to patterns you see on wallpaper and perhaps some of the dresses worn tonight. You get this repeating pattern. And this is what happens with these crystalline giant structures. But some of these materials, these crystalline materials, they're not solid in the sense that all the atoms or ions stay where they are. Some of the ions actually move. And this one, in green, is what we call a defect, an interstitial defect. It's in a position not normally occupied. So if you look at the screen and shake your head about, you're going to see an ion moving. You can give me an ooh if you like it. Ooh. So that's basically ion motion. This ion motion or ion conduction is very important in several applications. In batteries, in fuel cells, superconductors rely on often fast motion. But often the pathways within these crystals are very difficult to determine by experiment alone. And that's where modeling can come in. In fact, I like that video so much, I'm going to repeat it, but in 3. So this is showing examples of ion conduction in solids. So let me move on to, so those interstitial, that ion motion, I call them defects. So defects is actually the wrong word. It should be imperfections. All solids, all crystalline solids have defects in them in nature. And this is a quote from a colleague, Sean Corish, at Trinity College, Dublin. He said, like people, solids are imperfect, making them unique and interesting. And I show this beautiful painting by Salvador Dali because it reminds me of the combination of a crystal image and a person. And also reminds me that just like fine art, science can be just as beautiful and creative. The next quote is from me. Like solids, some people have more defects than others. I won't comment on those hairstyles, but I know I've got several defects. My wife says my dodgy puns, and you'll hear some of them along the way. So another important example of defects are what we call dopants, or in this case, impurities. Often materials are deliberately doped with impurities. In this case, the impurities produce these beautiful gemstones and this variety of colors. So they are, by nature, contain these impurity defects. Another good example is Walter White in Breaking Bad. His crystal meth, for TV purposes, was impure. The stuff I make is crystal clear. So it shouldn't be blue. I don't sell it. I just give it away, actually. So computer modeling. I mentioned modeling. So when I go to parties, that's when I get invited, that is. Somehow the invitations dry up when you mention you're a university professor. But anyway, when I get invited to parties, when people ask me, what do you do, Saiful? Sometimes I say, I model. And obviously, it's not modeling down the catwalk, but modeling on the vast supercomputers. So why do we need modeling? I'll explain what modeling is in a section. But we need modeling. It's a very important bridge between theory, pure theory, and experimental observation and evidence. And also, modeling can actually provide understanding of very complex materials or understand complexity in general. And a good example of this bridge between theory and experiment is this iconic photo of Watson and Crick in Cambridge back in 1953, where they used basically modeling. In this case, they were using clamps and retort stands to build up the molecule of life, DNA, and they worked out that it was a double helix. But they relied on experiment, and that experimental evidence was provided by Rosalind Franklin and her famous photo 51, an X-ray diffraction image. Sadly, she died before 1962 when the Nobel Prize was awarded, and I believe she should have been one of the three. So nowadays, you can actually do that on a supercomputer within seconds or minutes. You can derive that double helix structure, that beautiful double helix structure. And I mention those words at the bottom, fundamental research, and it's a reminder to me that this is a fantastic example of fundamental blue skies research. No one would have thought about what is your application of working out the structure of DNA. Well, now we know that in terms of modern biology, without knowing the structure of DNA, the double helix, we wouldn't have the advances that we have. So modeling. So I want to show you one more slide on materials modeling. So modeling can actually mean different things to different people. It relies on different length scales and different time scales. And this is a nice summary. Along the y-axis, along the vertical axis is the length scale, and along the horizontal axis, we've got the time scale. So right at the bottom left is really where physicists and chemists lie in terms of atoms and electrons. And then in terms of materials and tools engineering, you've got modeling of grains. And then really at the engineering, the top engineering end, you've got device modeling as well. So this is really different scales, and all scales have a range of modeling tools. Increasingly, we're using machine learning techniques, or in current parlance, AI techniques, to try and bridge the different scales. Because you've got a lot of data is generated at the bottom left. Can you use that data now to bridge those different scales? I won't go into the details, but I'm happy to talk afterwards about the details behind this materials modeling. I want to move on to the main course, which is energy storage and why lithium-ion batteries. Well, I'm going to start off with something I call the portal revolution, but another words for these is disruptive innovation. This is one of the most disruptive technologies out there. So when I went to concerts in the 1980s and 90s, when I went to see the Smiths or The Cure or New Order, that's what the audience would look like. Nowadays, if you went to see Taylor Swift, Coldplay, or Ed Sheeran perhaps, that's what the audience looks like. They're all carrying mobile devices. And it's not really a mobile phone. It is a mini supercomputer. And it's actually more powerful. It's amazing to think about it. It's more powerful than the computers that were used to send the Apollo rocket and Neil Armstrong to the moon back in the late 1960s. So there are these mini supercomputers, and it's led to this portal revolution. And really, what's powering that revolution is the lithium-ion battery. And so why lithium? So this explains why lithium. Up on the vertical axis is something called the volumetric energy density, how much energy you can store within a unit volume. So that's basically to do with size. And then along the horizontal axis is a specific energy density, how much energy you can store within a unit mass. So basically how heavy or light it can be. And you can see at the bottom left is the bog standard lead-acid battery. So you can imagine you can't stick your car lead-acid battery into your phone. And that's the reason why. The actual amount of energy you can store per unit volume or unit mass is not great enough. Then the nickel-cadmium, nickel metal hydride, and the lithium-ion on the top right. And that has really gone even further in terms of the actual values you can see. So basically, more than 3 times the energy density than the lead-acid battery you can store within a lithium-ion battery. And that has led to the next challenge is, can we decarbonize road transport? Can we get more electric vehicles? Oh, actually, yes. So the next challenge, as I said, road transport. So a couple of interesting statistics. I don't like to throw out lots of numbers, but I thought I'd mention 2 numbers. Road transport accounts for about 25 to 30% of all CO2 emissions in the developed world. And that is largely going to increase if you think about car ownership within China and India and Brazil elsewhere. The other interesting statistic is 90% of UK car journeys are less than 40 miles. In fact, I think 50% are less than 5 miles. So the supermarket run or the school run. So actually, this idea of range anxiety is actually just psychological. Most journeys you can do within the range of most electric vehicles. So there is this growth in electric vehicles. And if you think about any car manufacturer, adverts on TV, you're always seeing some hybrid electric vehicles. I suppose the pioneer was the Toyota Prius and their hybrid. Then just up the road, we've got Nissan Leaf being manufactured. There's Tesla. And I found this image of the electric Newcastle buses, the Voltra, and obviously Angel of the North mentioned in the background. I'm not a car engineer. I show this schematic not because of the car engineering, because I love the label at the top. It says battery recharge plug, not to scale. Can you imagine this large kind of plug right behind you? That will slow down your range. So the next question is, you might ask, Saiful, what's inside? Hey? Oh, how did that happen? Did I close it? Oh, no. Oh, there. Oh, I don't know why I did that. Anyway, so the next question is, you may ask, what's inside a lithium-ion battery? And I know there are some battery experts in the audience, but for the non-battery experts. So basically, a battery, well, most batteries, or all batteries, are electrochemical sandwich. And electrochemical sandwich means you've got 2 bread slices. In this case, a positive electrode, or sandwich bread slice, is the lithium-cobalt cathode. The other bread slice or electrode is the graphite anode. And you can see both of them are layered or sheet-like structures. Like any sandwich, you need a good sandwich filling. So the meat, or hummus if you're a vegan or vegetarian, is a good lithium-ion conductor. In this case, it's a lithium salt with an organic solvent. So how does it work? So when you're plugging in your phone or iPad tonight, basically you're going to be doing some chemistry in action. Lithiums, you're going to get electrons from the mains, and lithiums will move from your positive electrode to the negative electrode. Then when you're going to lose your device, when you're going to discharge your battery, you're going to use that stored energy, and electrons go round, and the lithium ions going from one electrode to the other. So it's basically an electrochemical reaction within that small device. Lithium ions are moving. I'll talk about lithium ions moving in a second. You would love that phone to be charged for maybe a month rather than having to charge it daily. So we need to store more energy within that material. And that means getting more lithium ions and more energy storage within these devices. So the pioneer behind the lithium-ion battery is John B. Goodenough. It was long overdue, he finally got the Nobel Prize in 2019 at the age of 97. For those who are not sure, John Goodenough is the one on the left. The one on the right is a scientist, a president who believed in science and the scientific method. The other two Nobel laureates, Stanley Whittingham in New York and Akira Ishino in Japan. John Goodenough did that pioneering work actually in the inorganic chemistry labs at Oxford in the 1980s. Sadly, he passed away this year at the age of 101, but such a pioneer in the field. He was asked about his favorite area. It wasn't even his Nobel Prize winning area. He made a big influence in magnetism in solids. So he was really a pioneer in so many different fields. So as I said, we need to store more energy. And one of the limitations of the lithium-ion battery is to do with the positive electrode, the cathode. So I'm going to mention some types of new material in the cathode. And it relates to the funding institution within the UK, which is called the Faraday Institution. This is funding a whole range of different lithium battery research, or actually battery research in general. In terms of chemistry, the hurdle for high energy density, as I mentioned, is the cathode. And I lead a Faraday Institution project called CATMAT, looking at next generation lithium-ion cathode materials. Our main objective is, can we develop higher energy density cathodes for high energy density lithium-ion batteries? So before I'm going to show you some 3D images again, this is to do with building blocks and with a dodgy pun. The name is bond, chemical bond. So what I'm showing you here is a simple building unit. On the top left is a metal ion in blue connected to 6 oxygens. And for those keen followers of material science will know that oxygens are in red. And that can be represented by an octahedron shown on the right in orange. Likewise, on the bottom left is a metal ion coordinated to 4 oxygens. And you can represent that by a tetrahedron or a pyramid type structure. And I mention that because if you're not familiar with those units, then you won't be familiar with the 3D images next. So if you get your 3D glasses on, you'll see a material that's in your phone right now. This is in your phone right now. So this is the layered sheet-like positive electrode based on lithium cobalt oxide. And you can see you've got these octahedra, cobalt oxide octahedra, edge sharing to form these sheets. And then in between, you've got these lithium ions shown as spheres. And those lithium ions can come out, in and out, as you're charging your phone. So in between those kind of cobalt oxide sheets, the lithium ions are coming out. So as in life, the important stuff is happening between the sheets. Sorry about that. So there, that is a 2D motion. The next image is a new, well, no, it's not a new material, but it's a material, I should note now, so cobalt, there's a problem with cobalt. Cobalt is expensive, toxic, and there are some ethical issues about its mining. So in terms of reducing that cobalt, they're trying to replace, or it has been done, replacing cobalt with other more abundant elements, nickel and manganese. And we're looking at what is called lithium-rich NMC. So NMC is short for nickel, manganese, cobalt. So these NMCs are currently used in electric vehicles right now. And we're looking at lithium-rich NMC because that has a higher energy density. We would like to move away from these elements completely and move to iron. Iron is abundant, it's cheap, and this is a beautiful structure called olivine. And the formula is lithium iron phosphate. But the olivine is a naturally occurring mineral. And as you can see, it's a very different structure from the layered structure I've shown you already. It's got these iron octahedra and phosphate tetrahedra. So that's lithium iron phosphate. And the lithium ions are in yellow, coming out. So if you shake your head about, you can see it's a very beautiful, connected 3D structure. So why is that topical? Well, that's topical, as I said, because of iron. Iron brings down the cost, and it's actually very abundant. It doesn't have as high energy density, but it is being mass-produced, and it's going to be used in some next-generation Tesla cars. So keep your 3D glasses on. This is part of a consortium. I was part of a research consortium that was linking our materials into practical batteries. And it was tested out on real vehicles. And you may not believe it, but this is a test vehicle in the engineering department at the University of Strathclyde up in Glasgow. And I show this because, as you can see from what they're wearing, it was a relatively warm day in Glasgow that day. So the next thing is, when I mentioned charging, I said to you that the lithium ions are charging and moving from one side of the battery to the other, between the electrodes. Ultimately, we want that charging to be much, much faster. So again, you would love to charge, rather than taking maybe a few hours to charge, you'd love to charge that within seconds. And obviously for electric vehicles, we'd like to just pull up and charge very quickly. And that relies on ion diffusion, the lithium ions moving. So this is some actual animation of some modeling. And actually, before I show it to you, the reason why modeling is very important in this area is that lithium is one of the actually, it is the smallest metal ion in the periodic table. It's the third element in the periodic table. So it's a tiny, tiny ion. So it's very difficult to probe by experiment alone. So actually seeing what lithium ions are doing in your battery can be very, very difficult. So this is where modeling can actually assist. So what I'm showing you here, I don't know if I can turn it, do I dare to turn it down one more? I'll do it just for a second, if I can. No? Oh. I'll come back in a second. So what I'm showing you here is that layered sheet-like structure. And as I said, the important stuff is happening there. So the red ions are oxygen, the blues are cobalt, and the greens are lithium ions. What we're showing you is some molecular dynamics simulation confirming, it's basically known, it's confirming that lithium ions are moving in 2D between those sheets. But it's moving, and what we can do is extract real quantitative data, how fast the lithium ions are moving. And the idea here is that can we then predict new materials that can have the lithium ions move even faster? So actually, I'll just do it for this one, and then I'll put the lights back on. So this is the lithium iron phosphate that I showed you before, the non-layered structure. And the same thing applies here. It wasn't certain how the lithium ions are moving. So the blues are the phosphate groups, the yellows are the iron octahedral groups, and the grey are the lithium ions. And if you took a guess, if you were speculating, you think, oh, the lithium ions probably move in that straight line connecting the two lithium, the different lithium sites. We found from modeling that it was linear. In terms of, it was 1D, one-dimensional, but in this case, the path was curved. It was a curved pathway, and this was a clear prediction within a complex material that we found a curved pathway. What was nice is that with a collaboration with a group in Japan, led by Yamada in Tokyo, we did some very careful neutron diffraction studies using what are called maximum entropy methods. But anyway, what it allows you to do is map out from experiment the lithium ion pathway, which I'm showing you here as a contour plot in blue. As you can see, it actually shows also a 1D curved pathway. And what was even neater, that there was actually really nice quantitative agreement between the density of the contour plot and our curved pathway. So I might have to turn the lights on because of, I think this is where I'll get it all wrong. Is that right? Right, there you are. So, not my research area, but obviously a question I get asked a lot is about resources and about mineral resources. So really, just like plastic and the whole plastic debate, there's the 3 R's for battery materials as well. We need to think about reducing, we need to think about reusing, and also recycling. And in terms of reducing, we want to reduce, obviously, the amount of material we use, but in particular, we want to reduce the use of cobalt. In terms of what we want to move to is earth-abundant elements like iron in particular, or silicon, and then end-of-life recycling. And this is where I think legislation is going to be very important. We currently have a legislative framework for lead-acid batteries. I think more than 95% of lead-acid batteries are recycled, and that should be the case for lithium-ion batteries. So really, these are resources that we need to think about for electric vehicles which are being mass-produced. So what about beyond lithium-ion? And I pose a question, what about sodium? So this is where I'm going to get to student audience participation. Hands up if you've heard about sodium-ion batteries. So there's a fair number, maybe about 1/4. But anyway, a number of you have heard about sodium-ion batteries. But that means 3/4 of you haven't heard of sodium-ion batteries, or just couldn't be bothered to put your hand up. So I'm going to get you to do some work. Sodium-ion batteries. So sodium is not just beyond lithium-ion, it's actually below lithium in the periodic table. It shares very much similar chemistry to lithium, but if there's going to be a fight between lithium and sodium, there's going to be some advantages and disadvantages versus lithium. So what I'd like you to do for the next 30 seconds, like a countdown clock, if I had the countdown clock, if you get the countdown clock out, then I want you to talk to your neighbours, and could you come up with at least 2, or maybe 2, advantages of sodium over lithium and disadvantages of sodium versus lithium. So off you go, 30 seconds, countdown. Right, I think we've had the countdown clock. That was 30 seconds. So these aren't obviously just the answers, but I'm going to produce 2 common answers for each. The advantages of sodium versus lithium is sodium is more abundant, so hence it's lower cost. So in terms of a cost issue, there is that. The main disadvantages, and that's to do with where it is in the periodic table below lithium, is that it has a greater mass and size versus lithium. So that means it's got a lower energy density, how much you can store. So you won't find sodium-ion batteries in the near future in your mobile phone, but you might find it in other applications. So the other applications being looked at is large-scale energy storage. So when the wind isn't blowing or the sun isn't shining, we need to store energy. Currently it's done by pumped hydro, but we might need to use other types of energy storage. And one of the ones mooted is large-scale sodium-ion batteries. The other area is sodium-ion batteries, because of the lower cost, they actually could be used for smaller vehicles, electric scooters or kind of e-bikes or small tuk-tuks in India. So that they are, and actually they've been used already. There's a company there, NIU, I think, in China, and a company in the UK, Freudian, are trying to commercialize sodium-ion batteries. So for those who haven't heard of sodium-ion batteries before, you have now, and hopefully you'll hear more about them in the future. So before I move on to dessert, a brief TV break. I was fortunate enough to be asked to present the BBC Royal Institution Christmas lectures. It was a great honour, it was a big surprise, and it's the most stressful thing I've ever done. I didn't have any grey hair then, I had more hair then, and but it nearly killed me off. But it was actually, I don't regret doing it, but it was a big challenge. Obviously the godfather behind the Christmas lectures was the great scientist Michael Faraday, who kicked them off in 1825 at our institution, but other greats have followed. And for the youngsters in the audience, they were a really big thing for my generation as we were growing up. We only had 3 TV channels to watch. And at Christmas, the Christmas lectures were a big thing. And in 1973, when I was 10, David Attenborough presented them live. I hear that he didn't want to do them because they were live, because he had to work with children and animals, and that's always dangerous. And then in 1977, Carl Sagan, another great scientist, gave the lectures on the planets, and then more recently, Alice Roberts on genetics and life. So I gave them, and I gave them in 2016, which was the 80th anniversary of the first TV lectures. The first TV lectures were in 1936, and coincidentally, they were broadcast and filmed at Alexandra Palace, just walking distance from where I grew up in North London, in Crouch End. So the intro to my lectures are this. I don't know if the sound is working, but hopefully it does. So I call it Supercharged, Fueling the Future. So I did 3 lectures on energy conversion, sort of generating or converting energy from one form to the other. Number 2 was energy in the body, and number 3 was about energy storage. They're online, and I don't blame you haven't watched them. You've got so much other Christmas treats to watch, but they are still online. So what part of the lecture on energy storage is that you can show how a battery works by using a school experiment, which is just using a lemon. So when life gives you lemons, you make a lemon battery. But we did this, and I said to the Royal Institution, I don't want to just do one lemon. I just want to go small. I wanted to go large, very large. And we did. We built the largest lemon battery the world has ever seen. I got my group to buy 1,008 lemons. We cut them in half to get 2016 lemon slices. So this was true cutting-edge technology. And the group said, the tough part wasn't putting the lemon kind of connections together. The tough part was putting the IKEA shelving together, actually. And we generated a Guinness World Record. We squeezed out 1,275 volts from those lemons. However, 2 years later, a group in Denmark broke my world record. So I'm not saying I felt sour or bitter about this, but I was approached by the Royal Society of Chemistry before COP26, and they said, we want to do something for schools. And I said, quick as a flash, I said, I want my bloody record back. So I said to them, so this gave me a new kind of zest for life. That's the last of my lemon puns. And we got a new world record in 2021 with 3,000 lemons. Don't tell the Danish group. So I've got a Guinness World Record certificate and a Guinness World Record. And this one, we generated 2,304 volts. And it's, as a nice Christmas gift, it's in the 2023 Guinness World Records manual, page 214. And if you want to see the video, there's a short video produced by the Guinness World Records. And if you go to YouTube and type in 3,000 lemons, the video comes up. Anyway, that's, as well as research, that's one of my proudest moments, getting this world record. So let me end, just a short dessert. For those Smiths fans out there, there is a light that never goes out, and that is this famous nuclear reactor. These are the last of the 3D images. So if you get your 3D glasses on. So this is a nuclear reactor, but this is a nuclear reactor. You have to, it's not, I don't think this is the best 3D image, but it still gives you an idea. And we all know what the sun looks like, but but it's sort of coming out. But this nuclear reactor is conveniently placed 150 million kilometers away, or 93 million miles away. And in true Michael Caine fashion, did you know that the amount of sunlight that hits the Earth's surface in 90 minutes is about the entire world's energy consumption for 1 year? So really, we've got this free, renewable, sustainable energy up there, this nuclear reactor, but we've got to harness that solar energy. So we live, you can keep the 3D glasses on, there's some 3D. So we live in a world of crystals, as I mentioned, and the most common crystals are silicate-based. So when you're sunning yourself on the beach with the sand grains in your palm of your hand, this is the structure in the palm of your hand, this silicon dioxide 3D image, and they're corner-sharing tetrahedra. But from that silica, you can make silicon. And silicon, as you know, is the dominant material used in solar panels right now. And this is the crystal structure. This was one of the title images. And you can see it's a tetrahedral structure. The silicon atoms are spheres, and they're connected to 4 other silicons. If you replace silicon by carbon, you get, thank you, you get diamond. So silicon is a very strong and stable structure, just like diamond. But the problem with silicon, it's not cheap or easy to manufacture high quality crystalline silicon that you need for solar panels. So we're looking at something new, and this is the what's new. So I hope if you shake your head about, you can see this is a beautiful 3D image of a mineral called perovskite. So I've given you quite a few bits of information. One of the words I want you to take away is the word perovskite. It's a naturally occurring mineral. It's based on calcium titanate. A number of the professors in this audience are looking at perovskite-related materials for fuel cells and membranes. But in this case, this one is based on the titanium-oxygen octahedra. They're connected at corners, and the gaps in between occupied by large calcium ions. But why is it topical? Well, perovskite is topical because of a new solar cell material. And this is the solar cell material. It's a complex hybrid. It's a hybrid material because it's inorganic octahedra, lead iodide octahedra. As you can see, the octahedra are the same. But instead of calcium ions in the center, you've got an organic cation, in this case, methyl ammonium. So this is methyl ammonium lead iodide, which is a bit of a mouthful, but that is one of the most studied materials in the last 10 years. It's got numerous publications, and the reason is it's got high efficiency. So I'll explain that. The next slide is the last 3D image, but it's got nothing to do with my research yet. And that's basically a wake-up call. It's got this lovely, it's a bit scary. If you move your head around, the antennae follow you around. It's actually, if you look at this, it's really creepy. So it really comes out at you if you stare at it for a while. So if you've fallen asleep, this will wake you up, hopefully. So that's a millipede, and I don't know if it's used in batteries or fuel cells, but I just thought I'd show it to you. So why perovskites? So perovskites, so before I move on to why, I should explain a particular property of photovoltaics and solar cells, something called power conversion efficiency. In simple terms, it's basically light in, electricity out. So it's the percentage of converting light into electricity. Obviously, we would love that number to be as high as possible. So what I'm showing you is along the vertical axis is that power conversion efficiency as a percentage, and along the horizontal axis is the year of discovery, or the year of measurements or certification. In blue, I'm showing you silicon. So back in 1985, it was about 15%. This is kind of a single junction silicon cell. And around now, it's hovering around just below 25%. So not really a massive advance, but there's been an advance. The perovskite, in contrast, was first discovered in 2009. It was languishing at 3% back in 2009. Then within 12, 13 years, we've had this unprecedented rapid rise in power conversion efficiency. It's unprecedented for a new material to go from 3% to now to beyond 25%. And that's why these perovskites are very, very topical at the moment. So what do they look like on the atomic scale? So basically, you've got that organic cation, that methyl ammonium. You've got the iodides in purple and the leads in kind of a goldy color. You can see, unlike silicon, it's actually much more floppy. It's actually a softer material. So in terms of listing the properties, it's a really good absorber. It's easy to make. It's actually lab synthesis. It's very low-cost synthesis. The charge transport, in terms of its photovoltaic properties, are very good. But the big problem, the big challenge, is long-term stability. And this is where silicon comes in. And this is what's happening next. So what's next? So instead of using purely perovskite or purely silicon, you're going to hear more about what are called tandem cells. And as the name implies, tandem involves two components, using both perovskite and silicon. And that's because it's the best of both worlds. You can absorb a much wider range of the electromagnetic spectrum of the sunlight. So this is a schematic of a photovoltaic cell. You've got a sandwich layer, basically glass at the top, some electrical contacts, a perovskite layer, and a silicon layer. And that is just a schematic of what is a tandem cell. And what happens is that when you shine light, photons, you've got different ranges of that sunlight energy can be absorbed by the perovskite and silicon absorbers. So you've heard it from me, hopefully first, if you haven't heard about these tandem perovskite silicon cells. And a spin-out company called Oxford PV are developing them, and they're manufacturing large scale from next year, 2024. So it's quite an exciting aspect in terms of manufacturing. So let me just begin to conclude. I was asked to say a bit about my journey rather than just my research areas. So it's really in the guise of who do you think you are? So let me start with life and education. So as Greg mentioned, I grew up in North London, a place called Crouch End. So it's a bit like the Crouch Enders. It was quite rough in the 70s. It's become very trendy now. In fact, Crouch End's now called Crouchond. I went to a state comprehensive called Stationers, which it wasn't. Some say it was quite a rough school. In fact, it doesn't exist anymore. It was closed down soon after I left. I'm not saying it was a rough school, but it's one of those schools that they used to check for knives as you went in. And if you didn't have one, they gave you one. And then I managed to escape that school and managed to get into University College London back in 1981. You could probably work out my age. That was more than 40 years ago. And then after my degree and PhD, I did a research fellowship at Eastman Kodak in New York. Again, for the youngsters in the audience, this is called photographic film. You may not believe it. We used to buy these kind of rolls of film, put them into a camera, take 24 or 36 photos. We had no idea what they looked like. Got them developed from Boots, and then discovered that half of them were rubbish. But that's what we used to do with photographs. And that made billions for Kodak. Nowadays, Kodak is obviously a shadow of its former self. And that's because of the D word, digital. So digital photography has killed off photographic film largely. I then, to my surprise, got an academic position at University of Surrey in Guildford, and then, to my greater surprise, became Professor of materials chemistry at Bath. And this is when I began to discover the words that I didn't know before, but did describe how I felt. Imposter syndrome. I was the only professor of colour in the department and in the faculty at Bath at that time. But it was a real honour, and it's great working in an academic environment. And then when we moved to Bath, our children were, Yasmin was 3, Zach was 1, and they, as I can say, they tolerated my defects. They're now much older. Yasmin and Zach have flown the roost and at uni now. I then, as I said, I was honoured and privileged to give the Christmas lectures, and then 2 years ago joined the Materials Department at Oxford. So it's been a varied but a really fruitful and rewarding career. So I'm going to conclude. I don't want to take up too much of your time. There'll be time for questions. Some concluding remarks. Well, first of all, if you want some more information about what I do, if you Google Saiful Oxford, you'll get my website. I'm on Twitter, still calling it that, Saiful Chemistry. If you want to do some selfies with the 3D glasses, you can hashtag 3D SpexChem, as others have done, like these people here. That was a schools lecture in the middle there. I think they formed a boy band now called 3 Dimensions. And these others, I don't know who they are, but they keep following me around with their 3D glasses. So I'm going to end with some comments. So what is the future energy landscape going to look like? Well, there's one thing certain about the future. It's uncertain. But I'm, by nature, an eternal optimist, and so I think that we're on the cusp of a new era in low-carbon energy. There are obviously some economic and political forces that are out of scientists' control, but I still feel that it's a really exciting time to be a scientist in general and a material scientist in particular. And really, as material scientists, we're facing the challenges of green energy and sustainability. So I'm going to end with the F word. So the F word isn't the F-bomb, but a word that's used often in university circles now, and that is the word feedback. We're expected to get some feedback. So I got some feedback on some of my undergraduate lectures, and I got this feedback from one of my students. He or she said, if I had only 1 hour to live, I'd attend one of your lectures. However, because it would feel like an eternity. On that note, thank you.